Welcome all. So, today we will resume our presentation on the energy absorbing materials. Okay. So, yesterday we saw the design principles. So, we will be reiterating the design principles for the impact resistant materials. Okay. So, there should be irreversible energy conversion. Okay. The plastic deformation should be maximized and the elastic rebound deformation should be minimized. Okay. What does it mean? It means that when a material undergoes the force deformation, okay, initially it starts like behaving like an elastic material, okay, and after that the plastic phase comes into picture. Okay. So, the total absorbed energy is compounded by the area under the curve. Okay. So, if it remains in the elastic phase, what will happen is that there will be transfer of energy to this system, but this energy will be transferred back to the system due to the rebound. Okay. But when the plastic deformation occurs, okay, the total energy will be absorbed by this energy absorbing system. Okay. So, in order to maximize the energy absorption capacity, okay, this area should be maximized, okay, and the elastic rebound thing should be minimized. Okay. There should be restricted and constant force. Okay. So, what happens during an impact event? During an impact event, there is a net transfer of the force occurs, okay, in a very short duration of time. Okay. So, what it does is that the body comes into very high acceleration. Okay. The acceleration can be as high as 4 to 5 Gs, okay, 4 to 5 Gs. Okay. So, the injury caused to the occupant, okay, like head injury and other trauma is governed by this high acceleration. Okay. So, our goal is always to minimize the acceleration that is occurring in the body. Okay. So, there is always a peak acceleration, okay, and in order to minimize the injury, this acceleration has to be kept under this peak acceleration value. Okay. Long stroke. Okay. So, there should be large deformation, okay, for greater energy absorption. Okay. This again binds to the first principle of having plastic deformation. Okay. Let us say we have a material, okay, where the plastic deformation is there, but it is very low, okay, and there is another material which has a plastic deformation as well as the total deformation is very large. Okay. So, here the area under the curve is more. So, we will always go for a large deformation material. Okay. There should be a stable repeatable deformation mode. Okay. So, this stable repeatable deformation mode ensures the reliability of the material system. Okay. It means that during any event, during a crash event, the material should behave in the expected fashion, okay, because the nature of the impact is very random. Okay. So, we always ensure that our material behaves in the expected mode, okay, and there is a high specific energy absorption. Okay. So, as we have seen earlier, the energy absorbed per unit mass has to be maximized. Okay. This ensures the efficiency of the given system. So, these are our design principles, okay, according to which we determine the efficiency of any absorbing system. Continuing ahead. So, we will define some of the constants here. So, one constant is called the coefficient of restitution. Okay. So, what does it do? The coefficient of restitution quantifies the elasticity of a collision between two given bodies. Okay. And it is also a measure of how much kinetic energy is recovered after impact. Okay. So, E is the relative velocity after collision divided by the relative velocity before collision. Okay. And it gives us a sense of how much kinetic energy is recovered after impact. So, let us say if E equals to 1, it means that the relative velocity before collision and the relative velocity after collision is same. Okay. So, this is given as a elastic collision. Okay. In this case, there is no energy loss. If E equals to 0, it means that the relative velocity after collision is 0. Okay. It means that there is a perfectly inelastic collision. Okay. So, in this case there is the maximum energy loss and the two bodies stick together. It can be evident from this one, since the relative velocity is 0, it means that the two bodies are sticking together. Okay. In the real world application, the coefficient of restitution lies between 0 to 1, okay, and it means that there is a partial energy recovery. Okay. So, this coefficient of restitution has a very nice application in the real world. Okay. So, what we do is that we use this theorem, okay, in non-destructive testing. Okay. So, as we have seen, if there is a body, okay, and there is a moving body like here. Okay. So, the coefficient of restitution, it gives a measure of how much energy is lost or how much energy is recovered after impact. Okay. So, let us say we have a impactor with a certain energy K, okay, and if this body, okay, is, let us say it lies between two phases, okay, rigid, perfectly rigid, and very flexible. Okay. So, it means that if it is rigid, okay, the velocity before and after will be same. Okay. So, it will be constituted as a perfectly elastic collision, there is no loss of the energy, and if it is very flexible, okay, then if these two bodies stick, okay, then it will be treated as perfectly elastic collision, but in real application this value will be somewhere here. Okay. So, we will use this theory for a application called non-destructive testing. In non-destructive testing, what happens is that the energy imparted by the given impactor is constant. Okay. The sum total energy is constant, and this value of E is measured, okay, and it is measured in terms of the number of rebounds, okay, that this impactor goes. Okay. If the body is very hard, okay, if the hardness is more, then it will be coming into this phase, the rigid body, and if the body is very flexible, then it will lie in the this sphere. Okay. So, here the rebound number will be more, okay, and here the rebound number will be less. Okay. So, measuring this coefficient of restitution or rebound number, we can talk about how hard this body is, okay, and depending upon the hardness of this body, empirically it is also related to the strength of the body. Okay. So, this is a non-destructive example of this phenomena. Okay. So, the coefficient of restitution has an application in non-destructive testing also. Okay. So, using this impact properties, we can infer about the relative strength of the system also. Okay. So, different impact phenomena has different application in different fields. Okay. So, this is a very nice example of coefficient of restitution applied to a non-destructive testing. Okay. Then comes the kinetic definitions. Okay. So, the ratio of impulses during restitution and compression phase. Okay. So, E can also be defined in terms of the ratio of the impulses during restitution and the compression phases. So, this is the ratio of the restitution impulse divided by the compression impulse. Okay. It has also a energy definition. So, this can also be defined as the ratio of elastic energy released during restitution to total deformation energy stored during compression. Okay. So, E is defined in terms of velocity also, E can be defined in terms of impulse also, and E can be defined in terms of energy also. Okay. So, what is the physical interpretation? A higher coefficient of restitution E means less energy is dissipated as heat, sound or plastic deformation during collision. Okay. It means that if the value of E is high, the loss is lower. Okay. So, let us look into an intuitive mathematical example. Let us say there are two equal masses of mass m, one at rest and the other having a velocity v naught. Okay. So, this one is at rest, v2 initial is 0 and this mass is coming with a velocity of v1 initial. Okay. So, after collision, okay, this can be expressed in the terms of the coefficient of restitution. Okay. And the total loss in energy can again be defined in terms of the initial velocity, mass and the coefficient of restitution. So, here we can directly see that if value of E is less, it means that more energy is absorbed by the system, Okay. So, this energy absorption by the system can occur in terms of plastic deformation, heat, etc. Okay. So, energy loss, okay. Let us say if the value of E is 1, okay, then this total energy loss goes to 0, okay, and if E equals to 0, okay, the value of K is maximum. Okay. So, this is same as we inferred earlier. Okay. Higher value of E means energy loss is less, and lower value of E means the energy loss is more. Okay. And in the real world application, E will lie between 1 and 0. It means that the total energy loss, okay, will lie somewhere between the elastic phase and the plastic phase. Okay. Moving ahead. So, irreversible energy conservation, okay, this we have already seen. Okay. Okay. So, we will skip ahead. Okay. So, now we will look into the inertia sensitive structures. Okay. So, what are the inertia sensitive structures? Inertia sensitive energy absorbing structures are those whose deformation and energy absorption under impact are strongly influenced by the inertia of the both striker and the structure itself. Okay. So, let us say there are two bodies, okay, of mass m1 and m2. Okay. So, if the energy absorption phenomena, okay, which occurs under impact, okay, if these are moving like this, and if the energy absorption quantity, okay, if it is influenced by these two masses, okay, okay, so then these structures are called inertia sensitive energy absorbing structures, okay, because their energy absorptions is directly dependent upon their mass. Okay. So, this type of structure exhibit a pronounced dependence of final deformation energy absorption on the impact velocity and mass ratio, okay, not just on the total input energy. Okay. So, they have a higher dependency on the final deformation and the impact velocity. Okay. Typical examples of this type of inertia sensitive structures are pre-bent crooked plates, some sort of thin walled tubes, and structure with steeply falling load displacement curve. Okay. If the load displacement curve exhibits some behavior like this, then this behavior is exhibited, then this type of structures come into the category of the inertia sensitive structures, okay, because their energy absorptions will be a function of this mass as well as the impact velocity. Okay. So, type of energy absorption structures, okay, we will categorize this thing into type 1 flat topped and type 2 inertia sensitive structure. As told earlier, if this type of behavior is exhibited, okay, then this type of structures are called as the inertia sensitive structures. Okay. So, here we can see there is a flat load displacement curve after the initial peak. Okay. So, here the energy absorption is less sensitive to impact velocity. Okay. So, this type of structures are circular rings tubes. Okay. Here there is a steep fall in the force deformation curve. Okay. So, these are very sensitive to impact velocity and the inertia. Okay. So, examples of this are pre-bent or crooked plates. Okay. So, velocity and inertia sensitive key mechanisms. Okay. So, what happens? So, during a dynamic response, okay, when impacted, okay, a portion of the kinetic energy is instantly lost due to inelastic collision and axial compression. Okay. So, once the impact occurs, okay, so the initial kinetic energy is instantly lost, okay, due to the inelastic collision and axial compression. Okay. So, let us say this type of tubes are there. Okay. So, in this type of tubes, okay, let us say it is something like this. Okay. So, after deformation it will be looking something like this, okay, with this shape. Okay. So, there is a axial compression occurring in this thing, okay, after the impact. Okay. After that the remaining energy is dissipated via plastic hinge rotation or global deformation. Okay. So, here two types of phenomena will occur. First, there will be an axial compression, okay, and after this the global deformation is going to occur. Okay. Let us say we have a beam like this, okay, and some plate is occurring like this. Okay. So, during the first phase this type of axial deformation will occur, and after that this thing will undergo a global deformation. Okay. So, this will constitute two type of mechanisms, okay. Axial deformation, okay, inelastic collision, and after that plastic hinge and global deformation. Okay. So, there will occur what is known as energy partitioning. Okay. So, the fraction of energy absorbed in each phase depends upon the mass ratio of the striker to specimen and not just impact velocity. Okay. So, how much energy goes into the first phase and how much energy goes into the second phase will depend upon the relative mass of the striker and the impacted body. Okay. And it will not be just function of the impact velocity, but it will depend upon both the things. Okay. So, for type 2 structures, okay, inertia sensitive structures, higher impact velocities with smaller striker mass for constant energy results in greater instantaneous energy loss and less energy available for the large deformation. It means that during the first phase, okay, the maximum energy will be dissipated, and in the second phase less deformation will occur in the global sense. Okay. What does it means during for the design part? For the design implication, it means that the inertia sensitive structures are most challenging to scale and predict using simple static model. Okay. So, simple static model has its limitation when it comes to the inertia sensitive structures. The initial imperfection like crookedness, okay, and the strain rate sensitivity of the material can further influence the inertia effect. Okay. As we have seen, this crookedness plays a greater part into the inertia sensitive structures, okay, and strain rate will also heavily influence the performance and the design of the inertia sensitive structures. Moving ahead, so we will look into some of the fundamentals. Okay. So, whenever we are dealing with this type of system, we always consider a single mass damper system. So, what is a single mass damper system? Let us say, look into a very simple example. Let us say we have a beam. Okay. So, we will now delve into a bit of dynamics, we will brush up our dynamics a bit, and we will try to define what is a spring mass system. Okay. So, let us say we have a beam, and let us say it is impacted, let us consider a static case first, okay, and then we will consider a dynamic case. Okay. So, both the beams are same beams. Okay. So, this is a static case, this is a dynamic case. Okay. Okay. Here let us say f has a function with time. Okay. So, in static case what will happen? Let us say this is a centrally loaded structure. Okay. So, now this is going to bend like this. Okay. In dynamics what will happen? In dynamics this system, okay, will bend something like this, okay, and this system is going to oscillate, okay, around the center it is going to oscillate. Okay. So, this type of behavior will be there. Okay. So, this type of behavior comes from the mixture of its fundamental modes. Okay. So, the first mode is going to look like this, second mode will look like this for this particular structure, third mode will look like this, fourth will look like this, and so on and so forth. Okay. So, the final deformation will be a sum total of all the modes. Okay. So, depending upon the scenario, this might constitute maybe 35%, this might constitute 20%, 18%, and so on and so forth. Okay. So, the final deformation will be a sum total of all the modes. Okay. So, in any given system there are infinite modes. Okay. So, in order to make our life very simple, we will consider only one mode. Okay. We will consider only one mode. Okay. So, let us say that we are considering the first mode. Okay. We are, for this particular case we are considering the first mode and we are leaving out all the modes. Okay. So, if we do that, okay, what will happen? So, here we are considering only the first mode. Okay. So, during the first mode, the total system signature, okay, will be given by the first mode only. Okay. So, let us say our forcing function looks something like this. Okay. So, the total response of the system will be looking like this. Okay. So, we are considering only the first mode. Okay. So, if we consider only the first mode, then what we do is that we assume that the entire mass of the system, okay, is concentrated at only at one point, okay, and the stiffness is given by this deformation mode. Okay. So, this constitute one mass, one spring. Okay. Let us forget the damper for now on. Okay. So, the mass is concentrated at one point, which is given by this mode, okay, and this is the mode shape and degree of freedom. We are considering the degree of freedom at the center. Okay. Let us say in this example the force is applied at the center. So, we are considering the total deformation u at center. Okay. So, u becomes my degree of freedom. Okay. So, the entire effect of the mass is concentrated at the center only. Okay. So, here we will get an effective mass and the stiffness will be given by this shape. Okay. So, from the statics we know that stiffness is defined as the amount of force required to cause a unit deformation. Okay. So, for this particular case, okay, to consider a unit deformation in the first mode, the stiffness is 48 EI over L cube, okay, from our statics class, okay, and this mass we can concentrate at the center. Okay. So, if we concentrate the mass at the center, then we can break our beam into two parts. Okay. So, this beam has m over 2 mass and this beam has m over 2 mass. Okay. So, we can concentrate our mass like this. Okay. So, this becomes m over 4, m over 4, m over 4 and m over 4. So, these two ends are restrained. Okay. So, the total effective mass becomes m over 4 plus m over 4. Okay. So, it means 0.5 of mass total. Okay. So, this way, okay, we can get our spring mass system. Okay. So, this entire physical system, okay, we have now broken down into a single degree of freedom system with one effective mass and one stiffness, okay, and the chosen degree of freedom is at the center and the chosen mode shape is the first mode. Okay. So, this will result into a what we call as a spring dashpot model. Okay. So, this is mass effective, this is stiffness effective, and after that we introduce a damping term also, okay, C, which is dependent upon the relative velocity between the system. Okay. So, m mass represents the equivalent mass of the system, me, and spring k represent the stiffness of the system, okay, ke, and this is a elastic system. Okay. So, the total strain energy is recoverable, okay, and the damper stores the absorbed energy. Okay. So, this energy can be in terms of the dissipated energy, can be in terms of heat and other systems. Okay. So, if we look into the, if we follow the D'Alembert's principle, okay, Ft is the externally applied load, okay, and U is the chosen degree of freedom. So, here x is chosen. So, we will choose x as the chosen degree of freedom x. Okay. So, if we break down this body, okay, this becomes k into x, this becomes c into x dot, here it should be x dot, this dot should not be here, okay, and then there is a pseudo mass and there is a force acting on the system. Okay. So, using this free body diagram we can derive the equation of motion. Okay. So, mx double dot plus cx dot plus kx equals to the forcing function f of t, okay, where this portion is due to the inertia, this portion is due to the damping, or it also denotes the absorbed energy, and this portion is due to the stiffness of the system, and this is the externally applied loading on the system. Okay. So, this is the fundamental of the dynamics that we will use in order to design our energy absorption system. Moving ahead. So, the energy components in the system. So, as said earlier, this will constitute the kinetic energy, okay. Potential energy will be stored in terms of the elastic energy, okay, that will be stored in the spring. Okay. So, dissipated or the damping energy is stored in the dampers. Okay. So, work done by the external force is given by this term. Okay. So, the total mechanical energy is the sum total of the kinetic energy and the potential energy, and the energy absorption is quantified by the energy dissipated by the damper or by plastic deformation in the real structure. So, in the real structure different mechanisms will occur like friction, plastic deformation, heat loss, sound loss, okay. And in the mathematical way it will be determined by the energy damper, okay, which will be a function of the relative velocity. Okay. So, moving ahead. So, let us do an example. Let us say that we have a mass of 2 kg, we have a spring constant of 800 Newton meter, okay. The damping constant is given by this term 8 Newton second per meter, and we have an externally applied load given by this function. Okay. So, this is a sinusoidal function. Okay. This is a sinusoidal function. Okay. So, now we write down the equation of motion. Okay. So, as we have seen earlier, we make our spring mass dashpot model, and degree of freedom is given by x. Okay. This is externally applied load, this is the pseudo force M equivalent x double dot, then spring mass dashpot model. So, kx cx dot. Okay. So, we rewrite this equation. Okay. So, mass effective is 2 kgs. So, 2 x double dot plus spring constant is 800. So, 800 x. Okay. Damping is 8 Newton. So, 8 x dot, and forcing function is 50 sin 10 t. Okay. And we are maintaining a force unit of Newton. Okay. So, this is in Newton, this multiplied by the acceleration will be in newtons, this multiplied by the relative displacement will be in newtons, and this multiplied by the velocity component will also be in Newton. Okay. Now, initial condition, let us say the initial condition as is given as the body is at rest. Okay. So, normally we can solve for the closed form also, but here we are using the Runge-Kutta method, okay, a mathematical model, okay, to solve this equation. Okay. And let us say that we have taken a time interval of 0 to 5 second and divided it into 1000 point increments. Okay. So, output we will get as displacement, velocity and external force, okay, and the energies are calculated at each time step. Okay. And we will use a numerical integration technique given by the Simpson's rule for the work and dissipated energy. Okay. So, these things can be easily formed in any of the software. We can use MATLAB, we can use Excel also, okay, to solve those things. Okay. So, these are very neatly defined in MATLAB also. Okay. So, they have a given function for doing the solution for the ordinary differential equations, and they have given a module for solving for the numerical integrations. Okay. Simpson rules and other numerical integration techniques are also readily available there. Okay. So, once we solve it, okay, so this is the displacement curve that we got using MATLAB. Okay. So, we used MATLAB here in order to plot this thing, same thing can be done using Excel also. Okay. So, this is the external force plot, this is 50 sin 10 t, okay, and this is the displacement response, okay, this is the x. Okay. It means that this is giving the response of the system, okay, when an external force acts on the system. Okay. And now, here we are showing the kinetic energy, potential energy and the total energy plot. So, the blue gives the kinetic energy, orange gives the potential energy, and red is giving the total energy plot. Okay. So, this thing can be used, okay, in, to check your solution also. Okay. You can check with the magnitude also, you can check with the time gap also. Okay. Okay. So, similar way the work done by the external force can be calculated and the energy dissipated by the damper can also be calculated. Okay. So, different quantities of interest can be calculated using this equations. Okay. So, again the forcing function is this one. Okay. So, if this is the forcing function, then the displacement will also follow the same signature. Okay. So, the displacement will have two components. Okay. One component will be due to the system frequency and other component will be due to the forcing function frequency. Okay. Okay. And we can plot the energies and we can plot the work done and the total energy dissipated by the system. Okay. So, here I will stop now. Okay. What is required is that please do this exercise so that you are comfortable with the solution of the simple mass deformation models. Okay. And also you make yourself familiarized with this simple spring mass damper model. Okay. So, this is given as a practice example. Okay. Thank you.